Hello, everyone. My name is Basel Shbita. I'm a PhD candidate at USC. This work was done at GE Research with my co-author and supervisor, Dr. Abba Moitra, and it was part of the Graphical Symbol Expression Network project that is part of DARPA's ReMath program. And it was done during last summer. So let's start by some intro. So cyber physical system, I'm sure you've heard of them. They are everywhere. These are physical systems that are controlled by computer-based algorithms. So think about your washing machines at home, car engine, elevator, dryer, etc. These all have different microcontrollers, and these microcontrollers include software. And software could be just a binary that does not have any documentation that exists somewhere, or it could have an actual code attached to it. And so when we need to debug and check these systems and analyze them for some legacy support or whatever it is that it's required, we require an expert. But that expert is usually an expert that knows a lot of mathematical concepts and different conceptual knowledge about those systems, and not necessarily knows how to code or how to understand the code in which they were designed. So, for example, this schema shows that there's like a PI controller, a proportional and integrator component. And the expert knows that, but he does not know how to bridge the gap between that and the code that exists in the system. So this is where we come in. So we want to be able to reverse engineer a legacy product. How can we do that? And how can we route different relevant parts in the software to experts? And how can we recover different mathematical expressions that exist in the software? So these are different questions we are trying to answer. So there are many challenges, such as low-level programming proficiency and domain knowledge. And we don't have any off-the-shelf solution for that. But we want to use AI to improve the understanding of those complex systems by the expert and help us debug the systems. So we want to bridge the gap between binary code analysis and domain SMEs. So we want to go all the way from binary to the expert, but we somehow need to bridge that because the expert is a human that understands higher level concept, and the binary is just a bunch of code blocks. So how do we do that? So the first pre-processing step we do is binary decompilation. In case we have a binary, we need to turn it into some sort of code. And then from the code, we have sort of like pipeline that takes it from a code to semantic model / a knowledge graph. So how do we do that? So the first step, we actually have predefined ahead of time a semantic model to describe any code statement in any file. And this is something that we have done only once. This is not something that you need to do for each component. This is pre-designed ahead of time. And we basically have a pre-designed model that describes any code statement. So for example, a node that has some sort of a function, the hyperedge is sort of like a code statement. It has a specific subgraph, which is like sub functions that it may call. Each one has an identifier, et cetera, et cetera. And think about like mathematical expression having different elements, sort of like a tree expression. So all of those things, their abstract description is in this file. So this is something we define once. And then if we have some sort of a decompiled C code, in this case, we actually change the code a bit so that it's understandable for the sake of the ease of the example. So in this case, there's integrator state and input, etc. In real decompiled code, we just have variable without actual meaningful names. So this is just for the sake of simplicity, we did that. And what we get when we describe those functions using the semantic model is basically a knowledge graph, or actually an OWL file that describes this knowledge graph. And this is our starting point for this problem. And this, what you see here is actually described in SADL. SADL is a semantic application design language. It provides an English-like language for building semantic models and rules. And this is basically automatically translated into OWL. Again, we get that for free by using SADL. OWL is web ontology language. It's a vocabulary built with RDF, resource description language, which is very standard in the semantic web. It's a structured and semantic language to describe resources on the web. So this is our starting point. And then the question we're trying to answer is actually, how can we leverage this semantic model / knowledge graph to perform knowledge acquisition and help the expert help us to discover things about the system and debug it? So our proposed solution is actually to generate annotation rules. And these annotation rules can describe different concepts that the expert wants to acquire or distinguish or be able to analyze. So how do we do that? We actually have a user interface in which the expert can pick different elements that describe the concept that he is actually looking for and wants to analyze. And then we do sort of a data transformation to describe those concepts. And then we use inductive logic programming. So let's talk about inductive logic programming for a second, for those of you who are not familiar. So ILP, inductive logic programming, is basically a branch of machine learning that deals with learning theories in a form of logic programs. It's sort of like an intersection of logic programming and machine learning. And the great advantage over other machine learning branches is that it requires a very small amount of data and labeled data to work. It uses expressive first order logic, and it takes a background knowledge into account. So even if you don't have enough examples to describe a specific concept, but you can describe that specific concept in first order logic, you can actually write it down and it will be used straight ahead. And this sort of a branch is used usually for classification and prediction, such as in bioinformatics and NLP. So, given a background knowledge and some specific observations that are positive and negative, we can actually generate and induce a general rule that is the hypothesis in this case that describes the concept. So in this example, we see that the background knowledge consists the following. So Alice is a builder, Bob is a builder, Alice enjoys Lego, and Claire enjoys Lego. But the only positive example is that Alice is happy. And the negative examples are that Bob and Claire are not happy, right? It's a negative example. And then in this case, the H, the hypothesis would be that anyone who's a builder and enjoys Lego is actually happy. So this is the induced rule, and this is what we want to apply in this case. So the problem definition, again, just to formalize it again, is that we want to generate classification rules for math and control concepts in CPS code. And our input is an OWL data, which is the knowledge graph describing the code, and positive and negative examples that we get from the user using a user interface. And then the output is basically a rule or a Prolog program that describes that rule. And the whole process we're exposing to the user is iterative in the sense that the user can keep picking examples that are positive and negative until they are satisfied. So here's an example. In this decompiled C code, the expert can choose 2 negative examples for a constant. And then it would say, hey, this error and integrator are not constant, but these KPM and KIM are constant. And then the expert chooses those as positive and negatives. This is the semantic model, the knowledge graph that describes this decompiled C code. And this is the magic box that we are working on that takes this knowledge, takes those examples, and generates a rule. In this case, it gets that constant. Statement is a content, it outputs a variable that is explicit, it's assigned once, it's inside a function C, and that function is not inside a loop. So we know that this is actually a constant. So the approach we actually suggest is basically a Pythonic model that takes the OWL data and basically generates the ILP data, generates the background file and the background knowledge. It exposes all the knowledge to the expert using a UI. The expert chooses the positive examples and the negative examples, and then basically the system generates the hypotheses. In our case, we used Aleph. It's just one specific ILP system. You can use any other system. For the sake of simplicity, we decided to use Aleph. You can read more about it in the paper. And then this process is iterative in the sense that we can refine choosing the examples until we are satisfied. Now let's dive into this model, which shows how we take the OWL data and get the different B, E+, and E- components for the ILP system. So inside the OWL to Aleph component, we have several modules. Each one is responsible for sort of like different functionalities or different steps in the process. So the first one is sort of like the triple manager. This is the mini database that consists of all the different knowledge graph triples, subject, predicate, object. We have a database of code statement. This is what we call hyper edges. And each one of those hyper edges it's associated with a variable and a function. It could be not associated with any variable at all, or even several variables, but it has at least one functionality. And we have in each one of those collection of records. So for the function, we have, for example, expression tree attributes, such as, it has sort of like a mathematical operator, for example, addition or division or subtracting elements. We have functionality block attributes, such as was it used in different functions or different subgraph functions, as we mentioned earlier. And we have the variable manager, which actually does disambiguation because the same variable could exist in different code blocks. So we actually do disambiguation to make sure we are talking about the same variable. We also have usage attributes, as in statistical usage of those variables, where they are assigned once, assigned several times, where they reassign, etc. And basically, we have the Aleph data manager, which sort of like materializes all this data into an Aleph or ILP-like format that we can actually leverage for the ILP system. And this background knowledge that we generate goes into the UI, in which the expert can choose the positive example, the negative example, and get these positive example file and negative example file. So this is what the Aleph program requires. It requires a .b file, which stands for the background knowledge. It requires a .f, which is facts. It stands for, I know F could be confusing with false, but it's actually facts. And N is for the negative examples. And this is run over Flask. So Flask is an easy to use web development framework for just going from simple Python to some sort of a UI. And this is how the final .b and .f.n file look like. So this is the .b file. We see that we have the hyperedge definition, that a feature is a hyperedge, and there's signatures for each of the functions. So the operator takes a node, and this one takes a variable, concepts for rules, how many inputs and outputs they have, the instance data. So this is where the actual C file comes into play. So for example, we have a hyperedge that outputs some sort of a variable. It also uses some functionality. The functionality has a specific operator, division in this case. So this is a very long file that is materialized from the original knowledge graph file, the semantic model, and using the different functionalities we talked about before. It just generates the materialized B file or the materialized Aleph data, ILP data. And then this is how the positive and the negative files look. They just say, here are good examples. Here are positive examples for a feature that corresponds to what we want to learn. And here are some negative examples to what we want to learn. And this is how the UI looks. So the user gets a bunch of statements, code statements, or hyperedges, and they can select if it's a positive or a negative. So these are added here, and then we can just generate all the files. And then we just run the ILP. So in the previous example, we've shown you the constant. So the first step, given those three examples we've shown before, two positives and one negative, we get the most specific clause, but this is not what we're interested in. We want to get the most reduced clause, which is describing the concept in the best way, but also simple. That would be both understandable by machines and humans. So this is the reduced clause we get in the first iteration. So it says that a new feature is a constant if it's a function, corresponds to a function that has a literal assignment. So we know that this is not necessarily true. So we can actually use the generated rule to query different statements in the code that correspond to this rule. And then using those, we can actually query them and see what they correspond to in the UI, and then choose more positive and negative examples. So this is the second iteration where we choose a literal assignment to something that is not constant, and we show another constant that is not necessarily a literal, and then we run it again, and we get a more accurate and a new reduced clause. In this case, it says a feature is a constant if it outputs a variable that is assigned once, and it uses a function C, and that function is not in a loop block. Sounds much more accurate and makes more sense. So this is the process, and you can keep iterating until you're satisfied with the result. And now let's talk about the evaluation. So in order to evaluate our approach, we constructed a data set that consists of 3 OWL files that include PI controller C, decompiled C code. It consists about 9,000 triples that covers 61 math and control concept instances that spans 9 different classes. So 61 instances for 9 classes. And these 9 classes are the above. So you see we have different sum, gain, division, PI controller, reference signal, etc. So what do you see in the result is that for 7 out of the 9 concept, we got actually a perfect F1 score. So we see that for all of the concept, the generated rule was generated in less than a second, which is great because we want fast and efficient iterative cycles for development between the expert and the analyst. We see that for 2 concept, we got actually a low F1 score, but you see that in the table, we see the original bottom class size and the reduced class size. So we see in all the perfect ones, we have a very major reduction and we have very good results. And we see that for these 2, for the output signal and the reference signals, there was no reduction at all because we couldn't reduce the class at all. And we didn't get a perfect F1 score, we do get perfect recall because that's the whole point of how ILP works, but the precision is not great. And this is because we did not have enough data or expressive data to separate the positive from the negatives. And that could happen from different reasons. So for example, the same code could be described or written in different ways. The same concept can be written in different ways. And this is something I will touch on in the next slides. But out of those perfect F1 score, let me show you an example. So here's one for the gain. So for the gain, we see that it includes a function. That function has an operator of multiplication. So it makes sense. And actually, it captured all of the instances in our code as accurate. And then we have constant. So this is the same one I've shown you before. We were kind of happy with it. And then if we look at the PI controller, even though it got a perfect F1 score, we see that it's not exactly describing a PI controller. It says like it has an implicit variable that goes, and that statement goes to a function that has the operator add. But we know that that not exactly describes PI controller. So in this case, if we had more examples in the data to select, we would have a better reduced clause or a more accurate description of the clause. So these are some notes for even the results that are complete. So the platform we've shown is feasible and effective in terms of time, completeness, and robustness. The results are satisfying. The quality of the ILP generated rules depends on the supplied input, but there are still many challenges. So local versus global variables is one example. So for example, we have enumerations and structures in the code, which is kind of challenging. We did not deal with pointers or inline code, so statements that are explicit versus implicit. Implementation style changes. This is something I mentioned previously about separating positive and negatives and having enough positive examples that are descriptive enough in different ways. So, you know, implementation style can vary. So if you think about a saturation component, we could have it implemented either in if-else style, or we can have it in more of arithmetic style. So both are valid, both are fine, but it just depends on the developer or how the decompiled code presented that. So yeah, looking forward, we can actually use the rules to fold them back into the semantic model and learn things from the semantic model side and induce rules from that part of the system, rather than doing that only in ILP side. So we can use probabilistic soft logic to on instance data to introduce more confidence on specific rules and not necessarily have it binary 1-0 in terms of like the clause is in or the clause is out. We can do joint classification. So imagine a situation where you can say, hey, there's only one PI controller in this code, and you want to encode that knowledge into your system. So we can do that as well. And then for augmentation, we can actually introduce, you know, memory allocation for the case of the pointers, or we can have layout features that correspond to sort of like implementation style features. So these are things that we can introduce in the future work. So as a conclusion, we've presented an automated platform for generating classification rules for math and control concepts in cyber-physical systems. The subject matter expert is not required to know the language formalism and describe the knowledge in detail. They can just select examples, as we've shown. It's a fast and iterative induction with human in the loop, so it's very efficient and useful. It's structured in semantics, so it makes it easy for machines and for humans to understand and read what's going on. It's easily extended and refined. We saw it either automatically by choosing more examples or manually by actually writing those rules and introduce them as background knowledge. And it's handy during design and engineering, right? You can incorporate feedback pretty fast and you can generate explanations if the subject matter expert is interested in that. And that is all for today, folks. So thank you for listening. If you have any questions, I'm available. Thank you so much. Enjoy the conference.